So, in the previous class, we looked at lead compensation, and we did an example as far as the design of the lead compensator is concerned. In today's class, I am going to introduce you to lag compensation, okay, when it is used, like what is the structure of a lag compensator and what are its features, right. And then we will also look at what effects does it have on the entire system, and we will also learn what is called as a lag lead compensator. Okay. So, I am just going to explain the concepts to you with respect to lag compensation and lead lag compensation. Okay. So, let us look at lag compensation. So, once again we consider unity negative feedback. Okay. So, the same structure that we adopted when we discussed lead compensation is taken here, right. So, the question becomes, when do we use a lag compensator, right. So, a lag compensator is typically used to attenuate or essentially reduce, right. So, the magnitude of high frequency components of the system's response. Okay. So, that is what a lag compensator typically components, okay, high frequency components of the system's response. Okay. That is the role of a lag compensator. So, what it essentially does is that it essentially reduces or attenuates the high frequency components of the system's response. As the name indicates, it introduces a phase lag, but by and large when you use a lag compensator, we are not unduly worried about the phase margins. Okay. So, the base system itself will have enough phase margin that the addition of a phase lag, see, phase lag means it is negative phase angle, right. So, obviously, like our phase margins are going to decrease a little bit, but we are not unduly worried about them, right. So, that is when you can apply a lag compensator, but then like we essentially want to attenuate the high frequency components, then we use a lag compensator and design the entire closed loop feedback system. So, let us look at the structure of a lag compensator. The controller transfer function or the transfer function corresponding to a lag compensator is the following. So, let us look at the structure. So, this is given by C of s is equal to Kc beta times Ts plus 1 divided by beta Ts plus 1. Okay. So, that is the transfer function corresponding to a lag compensator. Okay. So, this can be rewritten as Kc times S plus 1 over T divided by S plus 1 over beta T. And here of course, beta is greater than 1, T is greater than 0. Of course, we take Kc also to be greater than 0. Okay. So, that is the structure of a lag compensator. So, immediately we can see that this introduces an open loop pole at minus 1 over beta T and an open loop 0 at minus 1 over capital T, right. So, we can immediately observe that there is an open loop pole and an open loop 0 that is being introduced by this lag compensator. So, and what about the two corner frequencies? So, what are the two corner frequencies corresponding to this lag compensator? So, once again they are going to be 1 by T and 1 by beta T. Okay. So, those are the two corner frequencies corresponding to the numerator term and the denominator term respectively. Okay. So, that is what happens with the lag compensator, right. So, now let us look at the sinusoidal transfer function for this lag compensator. So, C of j omega will be Kc beta times 1 plus j T omega divided by 1 plus j beta d omega. Okay, so that's what is the sinusoidal transfer function corresponding to the lag compensator. Okay, so if we multiply and divide by the conjugate term of the denominator, so what we will get is the following. We will get kc beta times 1 plus beta times t squared omega squared divided by 1 plus beta squared t squared omega squared minus j times kc beta t omega times beta minus 1 divided by 1 plus beta squared t squared omega squared. Okay, so that's what we will have. Okay, pretty straightforward. So these are all like I am sure all of us are familiar with this process by now, right? I am just multiplying and dividing with the conjugate of the denominator, right? So that's what we do, right? So we can immediately note that as omega tends to 0, the transfer function essentially tends to kc beta, and as omega tends to infinity, the transfer function tends to kc. Okay, so you see that at either extremes, once again the imaginary component is 0, and so if you want to plot the Nyquist plot for the sinusoidal transfer function, so what can you immediately observe as far as the location of the Nyquist plot is concerned? The complex plane, let us call it as a CES plane. So what can you observe regarding the location of this Nyquist plot? So if you look at the real component and the imaginary component, right? So for all omega, you can immediately see that the real component is going to be positive, right? What about the imaginary component? Of course, leaving aside the two limiting values of 0 and infinity, it is going to be negative, or in general it is going to be non-positive, right? So which quadrant we are going to have this Nyquist plot in? The fourth quadrant, right? So in this complex plane, okay, that is where the Nyquist plot for this factor would lie in, right? So so we can immediately of course, once again this the locus is going to be in the form of a semicircle. So once again we can note that if I take the real part, okay, and subtract the center of this particular term, which is going to be kc by 2 times beta plus 1, okay, whole square. Because how did I get the center? Because the two limiting values are kc beta and kc, right? You take the mean of the two, right? So you will get kc by 2 times beta plus 1 plus I square the imaginary component kc beta t omega beta minus 1 divided by 1 plus beta squared t squared omega squared whole squared. That is going to be equal to what do you think should be the radius? I am sure by now we are all familiar with what is happening, right? So what should be the radius? Yeah, you just take the difference and divide by 2, right? So essentially you are going to get kc by 2 times beta minus 1 whole square, right? So that is what we are going to have here. So if we take the if you want to draw the Nyquist plot, the center is going to be at kc by 2 times beta plus 1, okay. So this is going to be kc beta. Please note that beta is greater than 1, right? And this is going to be kc, right? So what is going to happen is that the Nyquist plot is going to go something like this. Okay, so this is going to be a semicircular path, okay, and this is where it will start as omega tends to 0. This is where it ends as omega tends to infinity, right? And the radius of this particular semicircle is going to be kc by 2 times beta minus 1. Okay, so that is what is going to happen with the Nyquist plot of this particular sinusoidal transfer function. Okay. So now, if we continue, so I am going to leave you with a few exercise problems. Okay, this is pretty similar to what we did in the lead compensator. Okay, so you can see the analogy, like as you, or you can see the similarities and differences once you do the problems, right. So let's take, like the value of Kc to be 1, beta to be 10, and t to be 1. Okay, plot the Bode diagram of C of S, of C of j omega, all right. So that's what is the first exercise. Of course, I am going to give you the answer so that like we can discuss some concepts, right. So, but then like I am sure by now all of us know how to plot these diagrams. So, if I plug in these parameters, what is going to happen to C of S? I am going to get, please note that the transfer function for the lag compensator is Kc beta times Ts plus 1 divided by beta Ts plus 1. So, if I substitute, I am going to get 10 times S plus 1 divided by 10 S plus 1, right. So, that is what I will have. So, this I can rewrite as 3 factors, right, 10 S plus 1 and 1 by 10 S plus 1, right. So, that is what we are going to do. We are essentially going to plot the what you need to do is essentially plot the magnitude asymptotes for the log magnitude curves for each of these 3 factors and add, right. So, that will give me the net Bode plot, the log magnitude curve. So, I am just going to give you the answer straight away, right, so that we discuss it. So, what is going to happen is the following. So, this will start at 20 decibels, right. So, what are the 2 corner frequencies now? It is going to be 0.1 and 1, right, 1 by t and 1 by beta t. So, you will get the 2 corner frequencies as 0.1 and 1. 1 by beta t obviously is less than 1 by capital T, right, because beta is greater than 1, right. So, given the values, like we get the corner frequencies as 0.1 and 1. So, what is going to happen is that due to this contribution of 10, initially we will have 20 decibels till I reach 0.1, right, correct. Then what is going to happen? I am going to essentially have a down slope at minus 20 decibels per decade till I reach the other corner frequency, after which I will go for a horizontal line in the log magnitude curve, right. So, that is what is going to be the magnitude plot. I am just only drawing the asymptotes, right. So, that is what we are doing. So, I hope it is clear how we got it, right, because after the second corner frequency we add a asymptote with a positive slope of 20 decibels per decade. That cancels out the minus 20 decibels per decade. That is why we get a straight line beyond omega equals 1, right. So, that is what we have. Now, you can immediately see that from this particular Bode plot, you can immediately observe that this by and large acts like a low pass filter, right. So, it is essentially attenuating the high frequency components relative to the low frequency components, correct. So, that is the characteristic of a lag compensator, right. So, essentially of course, once again like plotting the phase diagram is something I leave it to you as an exercise, okay. Plot the phase plot for this particular transfer function, but immediately from this particular magnitude plot, we can immediately see that the the lead compensator acts like a low pass filter, okay. That's first observation. Then what else can we observe? Of course, there are 2 things, right. If I leave it the way it is, what is going to happen? The low frequency gains are going to be increased, right. Please note that if I keep this as C of S, I multiply with the Planck transfer function. What am I doing? At low frequencies I am adding 20 decibels, right. 20 decibels means, you know, like I am multiplying the gain by 100. Please remember, sorry, not by 100, 10, right, by a factor of 10. See, 20 decibels in the log magnitude curve means the factor is 10, right. So, that is what is the low frequency gain of this particular controller transfer function, correct. So, if I do this, what can you tell about the steady state errors? They will decrease, because the steady state, what to say, the low frequency gains will increase. Then you remember KPE, KVE and all those parameters will increase, which will reduce the steady state errors. So, you see that the low frequency gain increases. This implies that lower steady state error, okay. That is another feature. But on the other hand, if I do not want this, and then like if I want to essentially see, increasing the low frequency gain means, you know, like I am also the cost of the system also increases, right. But then if I want to really attenuate the high frequency components, what should I do? I should push down this curve, right, by 20 decibels, because look at this here, the high frequency components are left as they are. It is not really an attenuation. Of course, comparatively it is an attenuation, but on a absolute scale, the high frequency gains pass through as they are, right, the way this Bode diagram is drawn. But if I really want to attenuate the high frequency components, what will I do? I will just push down this Bode diagram by, let us say, 20 decibels for example, right. Then what is going to happen? The modified Bode diagram may look something like this, okay. It may shift down and go like this, right, if I want to really attenuate the high frequency components. So, if I do this, what is going to happen to the gain crossover frequency and the cutoff frequency? So, you immediately see that the gain crossover frequency, would it decrease or increase? It will decrease, right, because what is the gain crossover frequency? It is the frequency at which the magnitude of the open loop transfer function is 1, right. Now, I am pushing it down, right. So, I am multiplying the plant transfer function by a transfer function whose magnitude characteristics essentially are becoming lower, right, at this in this frequency range, right, lower than 1 in this frequency range. So, essentially what will happen is that obviously I will choose the corner frequencies in a frequency range of interest. That is what you will do when you do your case studies, okay. These are not arbitrarily chosen. The values of beta, t and all depend on the plant that you are given, okay. So, the corner frequencies are chosen in a sense way that it will be in a range or region around the original gain crossover frequency of the system that you are given, okay. So, now what will happen? The gain crossover frequency of the combined system or the compensated system will decrease. So, what will that mean? This will mean a reduced bandwidth, right. So, of course, reduced phase margin, of course, for us mainly what we are concerned about is reduced bandwidth also. So, of course, that is expected, right, because a low pass filter is supposed to attenuate the high frequency components, but the flip side is that when you try to do that, the bandwidth decreases. If the bandwidth decreases, the system's response becomes a little bit slower, right. So, that's a price we need to pay, right, if we want this feature, right. Please remember what happened in the lead compensator. We essentially increased the gain crossover frequency, the bandwidth increased, right. But what was the price that we paid in the lead compensator? It acted as a high pass filter, right. So, consequently, if I if I wanted to adjust the magnitude curve without amplifying the high frequency components too much, the steady state characteristics were affected. So, but here, you know, like it is a trade off, right. You can see that the Bode plot is just the the other way around, right. So, here we want to attenuate the high frequency components, the flip side is that what to say, the bandwidth decreases. Okay. So, that is a limitation with a what to say lag compensator. Okay. So, if you want to combine the advantages of both a lag compensator and a lead compensator, right, while addressing the limitation, like sometimes people use what is called as a lag lead compensator. Okay. So, what is this lag lead compensator, right? Please recall that if we use a lead compensator, improves the stability margins, that is, it improves the phase margins and so on, right. So, those are called as the stability margins. Okay. So, typically a lead compensator is designed to improve the stability margins, but may decrease the steady state accuracy, that is what we just discussed, right. So, that is a what to say, an outcome which is not desired, right, from a lead compensator. So, this may reduce the steady state accuracy. On the other hand, a lag compensator, right, so attenuates the high frequency components, but decreases the bandwidth, right. So, that is something we just observed. So, it can lead to a system with lower bandwidth or reduced bandwidth, right. So, hence sometimes like people use a lag lead compensator, right. So, just essentially to combine the benefits of both these compensators. Okay. It depends on the scenario, right. So, I am just going to give you the structure and then discuss it, and I will leave the Nyquist plot and Bode plot of the lag lead compensator as a homework problem, right. So, let us look at what is the controller transfer function. So, the transfer function of a lag lead compensator is, okay. So, how is the controller transfer function written? C of s is typically written as Kc times S plus 1 by T1 divided by S plus gamma by T1. Let me complete writing it, then we will discuss it. Okay. So, then multiplied by S plus 1 by T2 divided by S plus 1 divided by beta T2. Okay. So, that is the transfer function. So, here gamma is greater than 1, beta is greater than 1, T1 is greater than 0, T2 is greater than 0, of course, typically Kc is also greater than 0, right. So, of course, see when we discuss a lead compensator, we used alpha is less than 1. So, by conventionally, like when we talk about lag lead compensation, like that alpha is replaced by 1 by gamma. So, I am sure you can observe by now, right. So, alpha is less than 1, consequently gamma is greater than 1, okay. That is the only change. So, you can immediately see that this part. So, what I will do is that let me write this Kc factor just outside. So, you can immediately observe that this part is the lead compensator, it provides the phase lead, this corresponds to the lag compensator. Okay. So, that is the split between the two terms. Of course, you can immediately see that the complexity of the controller increases, right, is not it, right, because what you are having is now what to say 2 open loop zeros and 2 open loop poles being introduced by the controller transfer function, right. So, the design becomes more and more complex, right. So, but then it combines the advantage. So, sometimes you know like people may use it, and frequently we choose gamma to be equal to beta. Okay, so that's a typical design choice which is made, right? So that is the value of gamma and beta are chosen to be the same. So immediately you will see that the spread of the frequency range would be the same, because here you would see that the corner frequencies are going to be. So in this lead compensator, you will immediately see that what are the corner frequencies? It will be, there will be 1 by T1 and gamma by T1. So obviously gamma by T1 is greater than 1 by T1. See, previously we learned them as 1 by T and 1 by alpha T. Since 1 by alpha is now gamma, we just have it as gamma by T1. And for the lag compensator, the range of frequency is going to be 1 by beta T2 and 1 by T2, right? Those are the two corner frequencies. I am just writing the two corner frequencies. So if you choose gamma to be equal to beta, what's going to happen is that the range is going to be pretty much equal in the logarithmic scale, right? So that is essentially the ratios are going to be the same, right? As long as you know like you design what to say T1 and T2 carefully, of course, that's something which we need to do carefully, right? So that's another aspect we need to essentially look at.